The universe's brightest giants hide its most violent secrets. These are supermassive stars, cosmic powerhouses that shatter every rule we thought we knew. They are not the gentle twinkling lights of fairy tales, but volatile, mysterious engines driving the evolution of galaxies. In this journey, we will uncover 30 of their strangest behaviors, from stars flung across the cosmos to explosions that defy physics itself. By the end, you will see the night sky not as a static painting, but as a dramatic, living arena of stellar chaos. Why do some of these titans simply vanish without a trace, and what unseen forces twist their light into bizarre patterns? What single cosmic mystery would you most want to see solved in your lifetime? Our journey into the strange begins with stars that are literally running for their lives. Picture a stellar titan, millions of times brighter than our sun, being violently evicted from its home galaxy and flung into the endless dark. These are the runaway hypervelocity stars, and their existence is one of the cosmos' most dramatic escape stories. The primary suspect for this cosmic catapult is a supermassive black hole lurking at the galactic center. The most likely scenario involves a binary star system, two stars locked in a graceful orbital dance, wandering too close to this gravitational monster. The black hole's immense gravity can violently disrupt this partnership, capturing one star while violently flinging the other away at an unimaginable speed, like a stone from a slingshot. This gravitational slingshot effect can accelerate a star to over 1,000,000 miles per hour, fast enough to completely escape the pull of its entire galaxy. One famous runaway, known as HD 271791, is a massive star racing through the outskirts of our own Milky Way. Its trajectory and immense speed point directly back to a chaotic encounter in the galactic core. We can visualize its path, a solitary streak of light on a one-way trip into the intergalactic void. These stellar fugitives are not just cosmic curiosities. They are live ammunition, proof of the titanic forces at play in the hearts of galaxies, and a reminder that even the brightest giants are not safe from being cast out into the cold. But the drama of a stellar escape is only one facet of their violent nature. These same supermassive stars are engaged in a constant, furious act of self-destruction, shedding their own bodies into space at a staggering rate. This is extreme mass loss through stellar winds, a process so intense it defies all comparison to our own sun. Our sun emits a gentle solar breeze, a stream of particles that barely affects its overall mass over billions of years. A supermassive star, however, experiences a perpetual hurricane. The sheer power of the radiation generated in its core creates an outward pressure so immense that it literally blows the star's own outer layers away. This is radiation pressure in its most extreme form, where light itself pushes matter with enough force to overcome the star's tremendous gravity. The result is a stellar wind of unbelievable ferocity, carrying away mass equivalent to an entire planet like Jupiter every year. These winds are not made of simple hydrogen. They are laced with heavy elements forged in the star's nuclear furnace, scattering carbon, oxygen, and iron across space. We can observe this through spectroscopy, which reveals the unique chemical fingerprints of these elements in the light from the star. This ejected material doesn't just vanish. It piles up around the star, creating vast, glowing structures known as stellar wind bubbles. These are colossal shells of gas and dust, illuminated from within by the star's intense ultraviolet light. The star is essentially building its own funeral shroud, a brilliant nebula that marks the territory of a dying titan. This relentless shedding has a profound consequence. It drastically shortens the star's life. By throwing away its nuclear fuel at such an incredible rate, a supermassive star might live for only a few million years, a mere blink in cosmic time compared to the 10 billion-year lifespan of a star like our Sun. It is a spectacular, rapid burn, not a slow and steady glow, forever altering its own destiny and seeding the galaxy with the raw materials for new stars, planets, and perhaps even life itself. This furious shedding of mass creates a star that is fundamentally unstable, and that instability manifests in one of the most baffling behaviors of all: unpredictable and violent swings in brightness. While many stars pulse with a steady, reliable rhythm, these titans flicker and flare with a chaotic cadence all their own. Their light curves, the graphs that chart their brightness over time, look less like a gentle wave and more like the jagged peaks of a seismic reading during a major earthquake. The causes for these erratic tantrums are buried deep within the star's turbulent interior. One leading suspect is the sheer struggle between radiation and gravity. In a supermassive star, the outward pressure of light fighting against the inward crush of gravity can reach a fever pitch, creating massive instabilities in the star's core. These instances can trigger sudden, enormous convulsions that ripple through the entire star, causing it to brighten or dim without warning. Another possibility involves colossal magnetic activity far beyond anything our Sun experiences. Imagine magnetic fields so powerful they tie the star's atmosphere into knots, and when these fields suddenly snap and reorganize, they release catastrophic bursts of energy like a cosmic circuit breaker blowing. Sometimes the cause might be external. If the star has a companion, it might be gorging on material stolen from its neighbor. These accretion events, where vast amounts of gas suddenly rain down onto the star's surface, can ignite temporary but brilliant thermonuclear fires. No star exemplifies this chaotic behavior better than Eta Carinae, a monstrous binary system that is one of the most volatile objects in our galaxy. In the 1840s, it underwent a colossal eruption known as the Great Eruption, where it briefly became the second brightest star in the entire night sky, despite being over 7,000 light-years away. It did not go supernova, it simply threw a tantrum, ejecting the equivalent of at least 10 times the mass of our Sun, in an event that still defies complete explanation. Hubble Space Telescope images reveal the aftermath: the beautiful but violent homunculus nebula, two vast lobes of expanding gas and dust that were blown out from the star during that event. This nebula is the star's own ejected skin, a permanent testament to its instability. The star remains active today, its brightness still fluctuating unpredictably, a constant reminder that we are watching a ticking time bomb in the cosmic arena. What will it do next, and what other secrets of stellar violence are written in its erratic light? These erratic brightness swings are often choreographed by an invisible cosmic force, the star's own magnetic personality. While our Sun has a magnetic field that flips polarity every 11 years, the fields around supermassive stars are a different kind of monster entirely. They can be thousands of times more powerful, creating a chaotic and incredibly influential presence that dominates the star's entire existence. The generation of these immense fields is a turbulent process. Deep within the star, colossal rivers of superheated plasma, known as convection zones, churn and rotate at ferocious speeds. This movement of charged particles acts like a gigantic dynamo, generating magnetic fields of almost unimaginable strength. The resulting magnetic architecture is not a simple, orderly bar magnet. Instead, it is a tangled, chaotic web of magnetic field lines that erupt from the star's surface, arcing through its atmosphere in colossal loops and funnels. We can visualize these fields not with our eyes, but by studying the light the star emits. Instruments on telescopes like the Atacama Large Millimeter Array, or ALMA, can detect the subtle polarization of starlight, a telltale sign that it has traveled through these powerful magnetic structures. These fields do not just sit there, they actively shape the star's violent behavior. They are the primary sculptors of those extreme stellar winds we discussed earlier. The magnetic funnels act like channels, guiding and accelerating the outflowing gas, forcing it into specific streams and creating the vast, structured nebulae we observe. Without this magnetic guidance, the wind would be a more chaotic, spherical blast, but the influence of these magnetic fields also creates strange surface anomalies. Just as our Sun has sunspots, cooler and darker regions where magnetic field lines are particularly concentrated, supermassive stars have their own versions, but on a gargantuan scale. These are not mere blemishes, they are vast, tempestuous starspots that can cover a significant portion of the stellar surface, contributing to those erratic dips in brightness as they rotate in and out of our view. Some of the most dramatic magnetic anomalies are the colossal loops that rise high above the star's surface. These are not gentle arches, they are structures under immense tension, storing vast amounts of energy. When these magnetic loops become too strained, they can snap and reconnect in a catastrophic event, releasing a flash of energy that dwarfs our entire Sun's output for millions of years. This sudden release can trigger powerful flares and even contribute to the violent mass ejections that peel away the star's outer layers. So the next time you think of a star's brightness flickering, remember the unseen magnetic maestro conducting a symphony of chaos from deep within the stellar interior. The magnetic chaos on the surface is only amplified by the star's furious spin. Some of these cosmic giants whirl so fast they are literally on the verge of tearing themselves apart. This is the bizarre reality of stellar rotation, where the speed at which a star spins can completely reshape its destiny and its appearance. While our Sun completes a leisurely rotation once every 25 days, a supermassive star like Achernar, one of the brightest in the sky, spins at a breakneck pace. It rotates so rapidly that its equatorial diameter is more than 50% larger than its polar diameter. It is not a sphere, but a flattened, squashed oblate spheroid, a stellar pumpkin tumbling through space. This state is known as critical rotation, the absolute maximum speed a star can have before centrifugal forces overcome gravity, and the star flings its own material into space. The implications of such a furious spin are profound for the star's internal structure. This rapid rotation induces something called differential rotation, where the star's equator spins at a different rate than its poles. This creates colossal shearing forces in the stellar plasma, like different layers of a fluid moving against each other. This churning motion acts as a gigantic blender, stirring the star's interior and dredging up elements from the core that would otherwise remain hidden. Fresh nuclear fuel is mixed inward, and the byproducts of fusion, like helium and nitrogen, are brought to the surface. This process dramatically alters the star's chemical fingerprint and can extend its life by preventing a buildup of inert material at its core. For the fastest spinners, this centrifugal force is so powerful it can win the battle against gravity at the equator. Instead of a spherical stellar wind, the star sheds material primarily from its bulging midsection, forming a stable, rotating belt of gas around its waist known as a decretion disk. This is not an accretion disk where material is falling in, but the opposite, a disk of material being spun out and held in place by the star's own rotation. We can observe this directly around stars like Alpha Eridani, the formal name for Achernar, where the expelled gas forms a hot, glowing ring. Yet not all supermassive stars follow this pattern, and this is where the mystery deepens. Some of these titans rotate surprisingly slowly, a phenomenon that is just as puzzling as the hyperspinners. How does a star that formed from a collapsing, spinning cloud of gas end up with such a lethargic turn? The answer may lie in hidden companions or powerful magnetic fields acting as a cosmic brake, sapping the star's rotational energy over millions of years. This slow rotation creates a completely different internal environment, one without the efficient mixing of the fast spinners. The core becomes stratified, layered like an onion, with fusion products trapped at the center. This leads to a very different evolutionary path, likely resulting in a different kind of supernova or a massive black hole. So the simple act of spinning, whether frantic or sluggish, writes a crucial chapter in the life story of a supermassive star, dictating its shape, its chemistry, and its ultimate fate in the cosmos. This frantic spin does more than just reshape the star, it fundamentally alters its very chemistry. The surfaces of these supermassive stars often reveal a bizarre and exotic composition, a chemical fingerprint that defies the normal rules of stellar makeup. While typical stars like our Sun are primarily hydrogen and helium with just traces of heavier elements, these giants can have surfaces enriched with strange overabundances of elements like helium, nitrogen, and even rare metals. This phenomenon is written in their light, in the unique patterns of their spectral lines that act as a cosmic barcode. When astronomers break a star's light into a rainbow-like spectrum, dark lines appear at specific wavelengths, each one corresponding to a particular chemical element absorbing light. In many supermassive stars, the lines for helium and nitrogen are startlingly strong, while the lines for hydrogen and carbon are strangely weak. This tells a story of profound internal transformation and violent mixing. The engine for this chemical strangeness is the relentless nuclear furnace in the core, combined with the churning motions we call convection. In a star's heart, hydrogen is fused into helium through nuclear fusion. In a normal, slowly rotating star, that helium mostly stays put, accumulating as ash at the center. But in a supermassive, rapidly spinning star, the intense internal churning acts like a gigantic elevator, dredging this helium up from the core and carrying it all the way to the surface. This process, known as rotational mixing, brings the hidden products of nuclear burning into plain view. Sometimes the story gets even more complex. When helium itself is fused in the core, it creates carbon, and a subsequent series of reactions can transform that carbon into nitrogen. In stars where this internal mixing is exceptionally efficient, we see surfaces almost completely stripped of their original hydrogen, now dominated by helium and nitrogen. These are known as Wolf-Rayet stars, cosmic powerhouses shrouded in their own violently ejected atmospheres, their spectra screaming with the signs of exposed nuclear burning layers. The nucleosynthesis pathways do not stop there. In the most massive and evolved of these stars, successive stages of fusion can create oxygen, neon, and even heavier elements. The specific mix of elements we see on the surface becomes a direct diary of the star's internal nuclear history, a record of which fusion reactions have been dominant and how efficiently the star has stirred its own interior pot. This exotic chemistry is not just a curiosity, it is a preview of the star's final contribution to the cosmos. The strange elements we see on their surfaces today are the very same materials that will soon be blasted into space, eventually to be incorporated into new generations of stars, planets, and perhaps one day into the building blocks of life elsewhere in the galaxy. This bizarre chemistry on the surface is a direct warning of the cataclysm brewing deep within the core. For the most massive of these stellar titans, the final act is not a standard supernova, but something far more strange and utterly violent, a pair instability supernova. This is an explosion so powerful and so complete that it leaves behind no remnant, no black hole, no neutron star, just an empty cavity in space and a scattered cloud of newly forged elements. The trigger for this ultimate self-destruction lies in a battle between light and matter itself. Inside a star with an initial mass between about 130 and 250 times that of our Sun, the core becomes unimaginably hot and dense. The radiation trapped inside, the photons, are so energetic that they begin to spontaneously transform. Their colossal energy, governed by Einstein's famous equation, literally congeals into pairs of electrons and their antimatter counterparts, positrons. This process is called pair production, and for the star, it is a catastrophic loss of support. Those photons were providing the radiation pressure that was holding the core up against the crushing weight of the star's outer layers. When they vanish, turning from light into particles, that supporting pressure suddenly drops. The star's core, which was already balanced on a knife's edge, instantly loses its fight against gravity. A catastrophic collapse begins, but it does not lead to a rebound, as in a normal core collapse supernova. Instead, the infalling material compresses the core so rapidly and heats it to such an extreme temperature that runaway oxygen fusion ignites like a thermonuclear bomb deep inside the star. This is not a collapse followed by a bounce, it is a total thermal runaway. The energy released from this explosive oxygen fusion is so immense that it does not just blow off the star's outer layers, it completely and utterly unbinds the entire star. There is no gentle fading of a remnant. The entire stellar structure is vaporized in a single titanic blast. The energy released can be staggering, up to 100 times more powerful than a typical core collapse supernova, briefly outshining its entire host galaxy. Computer simulations of these events show a shockwave of unbelievable ferocity propagating outward, tearing the star apart from the inside out and scattering a tremendous amount of newly synthesized heavy elements like radioactive nickel into the cosmos. The light curve of such an event, the graph of its brightness over time, is distinct. It rises slowly, peaks incredibly high, and remains luminous for a very long time, powered by the decay of all that freshly created nickel. Finding a real-world example of such an event has been a major quest for astronomers. A leading candidate is the supernova known as SN 2007b, an explosion that was abnormally bright and long-lasting, matching many of the predicted signatures of a pair instability event. Its light curve and the sheer amount of nickel it produced point toward the complete destruction of a truly monstrous star. To witness such an event is to see the final, defiant act of a star so massive that it could not even leave a corpse behind, a true ghost in the cosmic machine. Yet the ultimate self-destruction of a pair instability supernova is not the only way these giants convulse. Some supermassive stars experience violent, repeating tantrums that strike not with a final bang, but in a series of furious eruptions. These are quasi-periodic eruptions, a rhythmic yet unpredictable drumbeat of violence echoing from deep space. The pattern is strange. It is not the perfect metronomic ticking of a clock. Instead, these outbursts repeat every few months or years, but the timing is slightly off, and the intensity of each blast varies wildly. It is the cosmic equivalent of a geyser, building pressure and releasing it in colossal bursts that are similar but never identical. One leading theory points to instabilities in the star's own nuclear furnace. Deep within these titans, nuclear fusion may not occur in a single, stable core. Instead, it can ignite in concentric shells like layers of an onion burning one after another. A shell of helium, for instance, might become unstable, undergoing a sudden, explosive burst of fusion. This shell burning creates a thermal pulse that violently expands the star's outer layers, causing a massive eruption and a huge increase in brightness. After the fuel in that shell is temporarily exhausted, the star contracts only for the cycle to begin again as fresh material drifts down and reignites the process. Another compelling idea involves a hidden dance with a companion star. In a tight binary system, a supermassive star might be slowly siphoning material from its neighbor. This stolen gas does not fall evenly onto the giant's surface. Instead, it accumulates in a vast disk, building up until it reaches a critical temperature and density, at which point the entire reservoir ignites in a runaway fusion reaction. This would release a tremendous flash of energy, a quasi-periodic eruption, before the cycle of accumulation and ignition starts all over again. Recent observations from space telescopes like Chandra and XMM Newton have caught these events in the act, not in visible light but in high-energy X-rays. These detectors see the incredibly hot gas, heated to millions of degrees during an eruption, something that would be invisible to our eyes. The data reveals the telltale, repeating spikes of energy, each one a catastrophic release of power that can outshine the star's normal output by a factor of 100. The impact of these eruptions on the surrounding space is profound. Each blast wave slams into the interstellar medium, the thin gas and dust that fills the void between stars. These shockwaves act like cosmic snowplows, compressing the material and triggering the collapse of cold, dense clouds. In doing so, these violent, repetitive outbursts can actually initiate the birth of new stars, a destructive act that paradoxically leads to creation. The star is not just dying, it is rhythmically pounding its surroundings, shaping its galactic neighborhood with every furious beat. The rhythmic eruptions of a solitary titan are dramatic enough, but many of these stellar monsters are not alone. They are born into a gravitational embrace so tight it defies belief, locked in a dance with another supermassive star. These are supermassive binary systems where two cosmic powerhouses orbit one another, their fates permanently intertwined in a relationship of extreme violence and strange consequences. The formation of such a system is a puzzle in itself. How can a single, collapsing cloud of gas fragment to produce not one, but two or even three stars of such immense size, all within a very small orbital space? The prevailing theory suggests that the initial protostellar disk, the swirling pancake of gas from which the stars form, is so massive and unstable that it spontaneously breaks apart under its own gravity, seeding multiple colossal cores right from the beginning. Once formed, the dynamics of this binary dance are anything but gentle. The gravitational pull between the two stars is immense, leading to powerful tidal interactions. Just as the Moon's gravity stretches Earth's oceans, each star exerts a tremendous force on its partner, distorting their shapes into teardrops rather than perfect spheres. This constant gravitational tugging transfers energy, synchronizing their spins and circularizing their orbits over time, locking them into a precise, intimate ballet. The most dramatic consequence of this close partnership is mass transfer. In many of these systems, one star will evolve faster than the other, expanding into a supergiant phase. When this happens, its outer atmosphere can spill over the gravitational boundary known as the Rochlobe, the point where the star's own gravity loses its hold. This stream of stellar material, a river of superheated gas, then flows directly onto the companion star. The receiving star gorges on this stolen fuel, which can dramatically alter its own evolution, making it more massive, hotter, and potentially spinning it up to incredible speeds. We can observe this process indirectly. The light from these systems often shows periodic eclipses as the stars pass in front of each other from our point of view. More tellingly, their spectra reveal Doppler shifts, the subtle stretching and compressing of light as the stars move toward and away from us in their orbit, allowing astronomers to calculate their masses and separation with remarkable precision. Detecting these systems is a monumental challenge because they are often shrouded in the very material they are exchanging, hidden within thick clouds of dust and gas. Yet finding them is crucial, for these binary pairs are the prime suspects for the most energetic events in the modern universe. The ultimate fate for many is a violent merger. As they orbit, they lose energy through gravitational waves, those ripples in spacetime predicted by Einstein, causing their orbits to slowly decay. Over millions of years, they spiral inward until their surfaces finally touch, triggering a cataclysmic union that can result in a single, even more massive star or a colossal stellar explosion. For the very closest pairs, the final merger of two supermassive stellar cores is one of the universe's most powerful predicted sources of low-frequency gravitational waves, a silent tremor in the cosmic fabric that future observatories hope to detect. The dance of these binary titans is a story of shared life, stolen mass, and an inevitable, explosive end that echoes across the fabric of spacetime itself. The violent dances of binary giants generate an invisible firestorm, a torrent of high-energy radiation that floods space with X-rays and gamma rays. This enigmatic emission is a signature of processes so extreme they push the very limits of physics, and standard stellar models fail to fully account for their sheer power. One of the most potent sources is the colossal shock of colliding winds. In a binary system where both stars are supermassive, each blasts out its own hurricane-like stellar wind. When these two supersonic outflows smash into each other, they create a chaotic region of impact where gas is heated to temperatures of tens of millions of degrees. It is a perpetual, invisible thunderhead where the collision converts the raw kinetic energy of the winds directly into a brilliant, high-energy glow, primarily in X-rays. The Chandra X-ray Observatory has given us stunning images of this phenomenon, revealing intricate structures of hot gas swirling between the stellar partners, their intensity fluctuating with the orbital dance of the stars. But colliding winds are not the only explanation. Some solitary supermassive stars also pump out surprising amounts of high-energy light, pointing to powerful magnetospheric processes. Imagine the star's own magnetic field, a tangled web of unimaginable strength, trapping and accelerating charged particles in its grip. These particles, whirling at nearly the speed of light along the magnetic field lines, then slam into the star's own dense atmosphere, releasing their energy in a burst of X-rays in a process known as magnetospheric emission. Then there are the most puzzling cases where the high-energy signal points to an unseen vampiric partner. Some supermassive stars are in a lethal embrace with a compact object, a neutron star, or even a black hole. In these systems, the star's powerful wind doesn't just collide, it is actively captured and devoured. As this stolen material spirals down onto the incredibly dense companion, it is heated to such extreme temperatures that it radiates not just in X-rays, but in the even more energetic realm of gamma rays. The Fermi Gamma Ray Space Telescope has detected such signals from several massive star systems, confirming that some of the most luminous gamma-ray sources in our galaxy are, in fact, these unbalanced stellar couples. The greatest mystery, however, comes in the form of sudden, unexplained flares. Instruments have recorded colossal spikes in X-ray and gamma-ray output from known supermassive stars, outbursts that appear and vanish over just hours or days. These are not the predictable pulses of colliding winds or steady accretion. They are violent, singular events like a cosmic switch being thrown. What could cause such a rapid and immense release of energy? The suspects are dramatic, a massive magnetic reconnection event, far larger than any solar flare, where the star's entire magnetic field suddenly snaps and reconfigures, or perhaps a catastrophic instability in an accretion disk, dumping a vast reservoir of material onto a compact companion all at once. Each of these high-energy photons carries a message from the most extreme environments nature can forge, a silent scream from the edge of a stellar abyss. This invisible high-energy firestorm is matched by a deep, resonant drumming from within the star itself. The surfaces of these titans often pulse and vibrate with complex rhythms, a form of stellar music that holds the key to their hidden interiors. While many stars have a steady heartbeat, the pulsations of supermassive stars are a chaotic symphony of strange harmonics and non-radial modes, where the entire sphere of the star ripples and distorts in intricate patterns. Scientists study these vibrations through a technique called asteroseismology, which is like listening to the music of a star to understand its internal structure. By breaking down the star's flickering light into its component frequencies, astronomers create a sort of musical score, a frequency diagram that reveals the pitch and intensity of each vibrational mode. A simple radial pulsation is like a single, deep drumbeat where the entire star expands and contracts uniformly, but the non-radial modes are far more complex. Imagine the surface of the star not just breathing in and out, but covered in rolling waves like the skin of a drum vibrating in multiple places at once. Some regions bulge outward while others sink inward simultaneously, creating a complex interference pattern in the starlight. One of the most famous and peculiar cases is the red supergiant Betelgeuse. In late 2019 and early 2020, it underwent a great dimming, its brightness dropping by over 60%, visible even to the naked eye. This was not a simple, rhythmic pulse. Follow-up observations revealed the cause was a colossal ejection of material that condensed into a vast cloud of starlight-blocking dust. But the event was likely triggered by an immense convective plume rising from the star's interior and coupled with a powerful pulsation. The star's own vibrations helped throw its atmosphere into space. To understand these sounds, we can translate them into a range we can hear. If we could listen to a supermassive star, its radial pulsations might be a low, resonant hum. But the non-radial modes would add higher-pitched tones, strange warbles, and chaotic beats, a cacophony reflecting the turbulent churning deep within. This stellar music is not just noise, every note carries information. The specific frequencies tell us about the star's density, its internal temperature, and the speed of sound waves traveling through its different layers. They can reveal the size of the convective core and the composition of the deep interior, details we could never see directly. Why do some stars pulse with such strange and unpredictable rhythms, and what other secrets are written in the silent, vibrating songs of these dying giants? The silent vibrations of a star would be a simple song if every giant followed the same cosmic score, but some of these titans break the most fundamental rule of all. For nearly a century, astronomers have relied on the mass-luminosity relation, a beautifully simple law stating that the more massive a star is, the brighter it will shine. It is the backbone of how we understand stellar physics, a predictable curve on a graph where mass increases along the bottom and luminosity rises steadily up the side. Yet when we place certain supermassive stars on this graph, they land far from where they should be, appearing as glaring outliers that defy the established order. Some blaze with a ferocious intensity that seems impossibly high for their measured mass, while others glow with a puzzling dimness as if holding back their true power. This anomalous relationship is a direct challenge to our understanding of how these engines work. One of the primary culprits is the star's furious rotation. When a star spins at a critical velocity, the centrifugal force at its equator provides an extra push against gravity's inward crush. This effectively makes the star less gravitationally compact, lowering the pressure and temperature in its core. A lower core temperature means the nuclear fusion reactions proceed less efficiently, so the star produces less energy than a non-rotating star of the same mass. It is a star that is massive but underperforming, appearing too dim for its weight class. We can visualize this on a theoretical graph. The standard mass-luminosity relation is a smooth, steeply rising curve. But for these rapid rotators, their data points would fall significantly below that line, clustering in a region that signals a hidden slowness in their internal fires. Conversely, the opposite effect can be created by powerful magnetic fields. A strong, ordered magnetic field running through the star's core can act as a conduit, channeling energy from the interior to the surface with incredible efficiency. This can make the star appear anomalously bright for its mass, as if its internal light is being focused and beamed outward. Its data point on our graph would float high above the standard curve, a beacon of unexplained excess. Then there is the problem of unresolved binaries. From a vast distance, two stars orbiting very close together can appear to our telescopes as a single point of light. If we measure the combined light and mistakenly assume it comes from one star, we would calculate an impossibly high luminosity and pair it with an inaccurate mass estimate, placing this phantom object far above the standard line on our graph. It is a cosmic case of mistaken identity, where what looks like one brilliant rebel is actually a hidden partnership. Astronomers must use sophisticated techniques like monitoring the subtle wobble in the star's spectral lines to unmask these deceptive pairs. The true nature of a star's power is not always written in its mass alone, but in the complex interplay of its spin, its magnetic personality, and the company it keeps. Each outlier on the graph is not a mistake in the data, but a clue pointing to a deeper, more intricate reality within. What other cosmic rules are these stellar titans quietly rewriting with their strange and brilliant lives? Rewriting the rulebook on stellar death, some supermassive stars refuse to go quietly into the night. Instead, they scream their final agony for months, even years before the main event, with violent pre-supernova outbursts that are completely reshaping our understanding of a star's last days. For decades, the prevailing view was that massive stars spent their final millennia in a state of relative calm before their cores catastrophically collapsed. But recent observations have shattered this peaceful picture, revealing a phase of frantic, desperate activity. The star seems to know its time is short, convulsing in a series of final, furious tantrums. This enhanced mass loss is one of the most dramatic signs. In its last years, a star can eject staggering amounts of material, far more than its usual stellar wind. Vast clouds of gas and dust are thrown off, forming a dense, opaque shroud around the star. This is the star literally tearing off its own outer layers before the core gives way. We can see this through spectral changes, the unique chemical barcode of the star's light. As the eruption unfolds, the spectrum shifts dramatically, showing new, broad emission lines that indicate fast-moving material and the presence of newly revealed elements from deep within the star. The most stunning confirmation of this violent pre-death phase came with supernova 2020 TLF. Astronomers were monitoring a red supergiant star in a galaxy not too far away when they witnessed something unprecedented. In the 130 days leading up to the supernova explosion itself, the star erupted with immense force. It threw off huge amounts of material, and its brightness surged, outshining its normal state by a significant margin. Telescopes captured the direct evidence of this pre-explosion outburst, a brilliant flash of light caused by the ejected material slamming into the dense cocoon of gas the star had created around itself in its final months. It was like watching a bomb's fuse ignite long before the detonation. This tells us that the final stages of fusion in the star's core are anything but stable. The core becomes a layered, chaotic factory with shells of silicon, oxygen, and neon burning in unstable, frantic waves. These convulsions send powerful shockwaves through the star's interior, violently shaking its outer envelope and blasting material into space. The entire stellar structure becomes seismically unstable, ringing like a giant bell until it can no longer hold itself together. This pre-supernova activity solves a long-standing mystery about some supernova remnants. When we look at the expanding shells of gas from ancient explosions, many are interacting with dense, pre-existing material, not the thin interstellar medium. We now know that material was likely ejected by the star itself in a final, desperate act of self-destruction. The star's death cry echoes long before the final collapse, a dramatic warning written in light and gas that we are only just beginning to understand. What other final secrets will these dying giants reveal in their last violent breaths? These violent pre-supernova outbursts are merely the prelude to an even grander and more terrifying finale. When the core of a supermassive star finally collapses under its own immense weight, it can trigger an explosion of almost unimaginable power, a hypernova. This is not just a supernova, it is a supernova on steroids, an event so energetic it can briefly outshine an entire galaxy and unleash a focused beam of destruction across the cosmos. The key ingredient for this cataclysm is a star with a mass at least 25 times that of our Sun, and one that is spinning with ferocious speed. As this titan exhausts its nuclear fuel, its iron core can no longer support itself against gravity's relentless crush. It collapses inward at nearly a quarter the speed of light. In a normal core collapse supernova, this inward fall rebounds off the newly formed ultra-dense neutron star core, creating a spherical shockwave that blows the star apart. But in a hypernova, the rapid rotation of the collapsing core changes everything. The infalling material does not hit a wall and bounce back evenly. Instead, the star's furious spin focuses the collapse into two powerful, narrow jets, firing out from the rotational poles at more than 99.9% the speed of light. These jets, composed of plasma and radiation, are the most relativistic outflows known in the universe, and they drill their way through the star's outer layers like cosmic blowtorches. The result is what astronomers call a collapsar, a rapidly rotating black hole formed from the stellar core, which acts as the central engine powering these jets for up to a minute. The entire star is not just exploding, it is being unzipped along its axis. The observational signature of this event is a long-duration gamma-ray burst, a flash of the highest energy light that can last from 2 seconds to several minutes. When one of those deadly jets is pointed directly at Earth, our satellites detect this brilliant, fleeting beacon from across the universe. Computer simulations of collapsars are breathtaking. They show the chaotic, swirling maelstrom of the collapsing star, the formation of the accretion disk around the newborn black hole, and the birth of those two pencil-thin jets piercing through the stellar envelope. The models reveal how magnetic fields, wound up by the incredible rotation, help to accelerate and collimate the jets, turning them into the most powerful particle accelerators in nature. Observational evidence for this incredible sequence of events is mounting. The afterglow of a long gamma-ray burst often reveals the fingerprint of a supernova, but one that is unusually bright and energetic, a hypernova. One of the most famous cases is gamma-ray burst 980425, whose afterglow clearly showed the spectral signature of a hypernova, linking these two phenomenal events beyond any reasonable doubt. These explosions are the primary forges for the heaviest elements in the universe, like gold and platinum, scattering them across galaxies. To witness a hypernova is to see the birth cry of a black hole and the violent end of a star that refused to fade away quietly, instead transforming its death into a brilliant, directional scream of pure energy. The death cries of hypernovas scatter the raw materials for cosmic structures, but long before that final act, a supermassive star is already a master sculptor. Its relationship with its immediate surroundings is a violent and creative partnership, forging intricate nebulae and disks that glow with the story of their birth. These circumstellar structures are not passive clouds, they are dynamic environments shaped by three relentless stellar forces. The first is photoionization, a process where the star's immense flood of ultraviolet radiation strikes the surrounding gas. These high-energy photons are so powerful they strip electrons from their atoms, creating a plasma of charged particles that begins to glow with its own ethereal light. This is the same principle behind a neon sign, but on a cosmic scale, painting vast nebulae in the specific colors of hydrogen, oxygen, and nitrogen. The second force is the star's own hurricane-like wind, which carves into the nebula, blowing vast bubbles and cavities. When a star is part of a binary system, the collision of its wind with that of its partner creates even more complex shapes with turbulent shock fronts where the two stellar gales meet. The third and perhaps most beautiful process is dust formation. In the cooler outer regions of these expanding nebulae, atoms can condense onto microscopic solid particles, creating cosmic soot. The Hubble Space Telescope has given us iconic views of these stellar workshops. Around Eta Carinii, we see the bipolar homunculus nebula, two vast lobes of gas and dust ejected during its great eruption, a perfect example of how a star's tantrum can forge a lasting monument. But the James Webb Space Telescope, with its infrared eyes, sees past the glare. It peers directly into the hearts of these dusty shrouds, revealing the complex chemistry and intricate structures hidden within. In the heart of the Tarantula Nebula, around the colossal star R13601, JWST sees the detailed physics of these violent interactions. It reveals how the star's radiation and wind are simultaneously eroding nearby dust pillars while triggering the birth of new stars within them. This is the duality of a supermassive star's influence, a cycle of destruction and creation happening side by side. The shapes we see are a direct diary of the star's activity. A spherical shell suggests a past steady wind, while a bipolar hourglass shape points to a dense disk around the star's equator, funneling the outflow toward the poles. These structures are temporary, destined to be blown away by the star's final supernova, but for a few million years they stand as brilliant, swirling testimonies to the power of a star to shape its own cosmic neighborhood. The light from a supermassive star carries a hidden message, a spectral fingerprint written in shifting lines of color and shadow. This is the realm of strange spectral line variability, where the absorption and emission lines in a star's spectrum flicker, widen, and morph in ways that reveal a cauldron of violent activity just beneath the surface. Astronomers use spectroscopy to break starlight into its component colors, creating a rainbow barcode where dark absorption lines indicate elements in the star's atmosphere soaking up specific wavelengths of light. In a stable star, these lines are steady and predictable, but in a supermassive star, they are a chaotic dance. These spectral convulsions are direct diagnostics of physical turmoil. When the lines broaden dramatically, it signals material being churned at ferocious speeds, often by the star's own furious rotation or by microturbulence in its seething atmosphere. When the lines shift in wavelength, it reveals the rhythmic in and out pulsations of the entire star, its surface moving toward and away from us. And when the lines change their very shape, splitting into complex components, it points to colossal magnetic fields or the presence of a clumpy, non-uniform stellar wind. The most peculiar and telling of these shapes is the P Cygni profile. This unique spectral signature shows a broad absorption line flanked by a bright emission line on its blueward side. It is the classic sign of an expanding atmosphere. The absorption is created when light from the stellar surface passes through the outflowing wind directly in our line of sight, while the emission comes from the glowing wind surrounding the star. In stable stars, this profile is consistent, but in volatile giants, the P Cygni profile can change unpredictably, its strength and shape shifting over days or even hours. This variability points to a wind that is not a smooth, steady flow, but a clumpy, chaotic torrent. Imagine the stellar wind not as a uniform river, but as a series of colossal cannonballs of gas being fired into space. These dense clumps form in the star's unstable outer layers, and as they move outward, they temporarily block different parts of the light, causing the absorption part of the P Cygni profile to deepen, weaken, or even develop multiple components. The star named P Cygni itself, a luminous blue variable, is the archetype for this behavior. Its spectrum has shown dramatic changes for centuries, with emission and absorption lines appearing, vanishing, and strengthening in an erratic ballet. This activity is a live report of the star's desperate struggle to hold itself together, its atmosphere boiling away in great, uneven gouts. Each flicker in its spectral lines is a cry from a star tearing itself apart, a real-time chronicle of instability written in a language of light that we are only just learning to decode. What other violent secrets are hidden in the ever-shifting spectrum of a dying titan? The chaotic light from these dying titans was not always a rare spectacle. In the universe's first chapters, supermassive stars were the original cosmic pioneers, and their violent lives fundamentally shaped the cosmos we see today. Their most profound role was in the epoch of reionization, the great transformation that lifted the universe out of its dark ages. For hundreds of millions of years after the Big Bang, the universe was an opaque fog of neutral hydrogen gas blocking light from traveling freely. The first stars, known as population 3 stars, are thought to have been monstrously massive, perhaps hundreds of times the weight of our Sun. When these behemoths switched on, they flooded the cosmos with its first intense blasts of ultraviolet radiation. This UV light was so energetic it began to strip electrons from the neutral hydrogen atoms, slowly burning away the fog and creating the transparent, ionized universe we inhabit. It was a cosmic dawn forged by stellar violence, yet the true behavior of these first stars presents a major puzzle. Standard models suggest a single, massive population 3 star could produce enough ionizing photons to clear vast bubbles of space. But the process was likely far more complex and messy. The same stars that provided the light also created powerful supernova feedback. When they died in colossal explosions, they blasted these newly cleared regions, shocking the gas and potentially disrupting or even shutting down the very star formation that created them. This self-regulating feedback loop, where a star's death prevents the birth of its successors, is a delicate balance that models struggle to get right. Did the first stars clear the fog steadily, or in violent, punctuated bursts driven by their explosive deaths? The James Webb Space Telescope is now peering back into this primordial era, looking for the chemical fingerprints left behind. Population 3 stars were made of only hydrogen and helium, the pristine elements from the Big Bang. When they died, they seeded the universe with the first heavier elements like carbon and oxygen. JWST is searching for the telltale signs of these uniquely ancient supernovae in the light of the most distant galaxies. It is also finding surprisingly bright and massive galaxies in the very early universe, objects that may have formed sooner than our models predicted. This could mean the first stars were even more massive and efficient at reionization than we thought, or that they formed in incredible, concentrated clusters, their combined UV output flooding the cosmos with ionizing radiation at a startling rate. The light we see from the edge of time carries the ghostly imprint of those first strange giants, whose furious lives and deaths wrote the very rules for everything that followed. The ghost of a pair instability supernova leaves behind a cosmic crime scene with no body. Unlike a typical supernova remnant, which often features a dense neutron star or a swirling pulsar wind nebula at its heart, the aftermath of a pair instability blast is an eerie emptiness. The entire star has been utterly annihilated, leaving only an expanding shell of glowing debris to mark where a titan once lived. This remnant is a vast, hollow bubble, its structure defined by the sheer violence of the explosion that created it. Inside, the cavity is filled with extremely hot, tenuous gas, while the leading edge of the blast wave plows into the interstellar medium, sweeping material into a dense, bright shell. The composition of this expanding cloud is its most revealing feature. Since the star was completely vaporized, the remnant is a rich soup of newly forged elements. Spectroscopic analysis reveals an overabundance of elements like oxygen, neon, and crucially, radioactive nickel. It was the decay of this nickel that powered the supernova's long, brilliant light curve, and its signature is now stamped across the remnant's glowing gases. These elements are not just sitting there, they are being violently dispersed. The expansion speed of these remnants is tremendous, as the initial explosion imparted so much energy that the debris continues to race outward at thousands of kilometers per second. This rapid dispersal is key to galactic chemistry. A single pair instability supernova can flood its local region of the galaxy with these freshly minted heavy elements, seeding future generations of stars and planets with the building blocks for rocky worlds and potentially life itself. Identifying such a remnant is a monumental challenge, as we are looking for an absence, a ghost in the machine. The best candidates are found in nearby galaxies with low metal content, environments similar to the early universe where such massive stars were thought to form. In the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, the remnant known as N1357 presents a compelling case. It is a vast, oxygen-rich shell with no central compact object expanding with incredible energy. Its chemical map, a plot of its elemental distribution, shows a striking concentration of oxygen and a lack of iron in its inner regions, a fingerprint that points directly to the complete disruption of a very massive star. To look upon such a structure is to witness the final, total sacrifice of a star, a cosmic phoenix that consumed itself entirely to enrich the void. This bizarre spectral dance finds its most dramatic expression when two stellar titans become locked in a lethal gravitational embrace. The transfer of mass between supermassive binary stars is not a gentle stream, but a chaotic, lopsided theft that can completely strip a giant down to its core. Picture a star expanding in its old age, its outer atmosphere swelling until it overflows its gravitational territory. This material, a river of superheated plasma, doesn't just drift away. It gets pulled by the gravity of the companion star, spiraling down onto its surface in a process known as Rochlobe overflow. The donor star is literally being cannibalized by its partner. In extreme cases, this can lead to a common envelope phase, one of the most violent and transformative events in stellar astrophysics. When the donor star expands too rapidly, the companion can't accrete the material fast enough. Instead of a neat stream, the recipient star plunges into the bloated atmosphere of its giant partner. The two stellar cores, the dense hearts of both stars, now orbit inside a single, shared envelope of gas. This is not a stable arrangement. Friction within this common envelope saps orbital energy, causing the two cores to spiral inexorably closer together. This immense friction also heats the envelope to incredible temperatures, driving it to expand even further. The vast majority of this shared gaseous shroud is then ejected into space, often forming a spectacular, rapidly expanding planetary nebula. The final outcome of this cosmic dance depends entirely on the initial masses and how close the spiral in brings the cores. Sometimes the entire envelope is ejected, leaving behind a much tighter binary system. We see the evidence for this in pairs like a hot helium star, the stripped-down core of the donor, orbiting a white dwarf or neutron star. In other cases, the spiral in doesn't stop. The two stellar cores merge into a single, rapidly spinning object. This merger can create a blue straggler, a star that appears mysteriously young and blue in an old star cluster, effectively rejuvenated by the influx of fresh hydrogen fuel. But the most exotic theoretical prediction is the formation of a Thorne-Zitkow object. This hypothetical hybrid star forms when a neutron star spirals all the way into the core of a red supergiant. Imagine a city-sized neutron star, denser than any material on Earth, orbiting deep inside a star so large it could engulf the orbit of Jupiter. The neutron star would act like a superheated rock in the center of a cosmic fireplace, altering the supergiant's nuclear fusion processes in strange ways. Theoretical models suggest the surface of such an object would be rich in unusual elements like lithium, rubidium, and molybdenum. For decades, astronomers searched for a star with this exact chemical signature, and one candidate, HV 2112 in the Small Magellanic Cloud, displayed many of the predicted traits. While its status is still debated, the hunt continues for these stellar chimeras, objects that are neither fully supergiant nor neutron star, but a bizarre fusion of both. The common envelope phase is a stellar crucible, a brief, violent epoch that forges entirely new classes of celestial objects from the wreckage of two stars. What other strange hybrids are waiting to be discovered in the aftermath of these cosmic collisions? The predictable life of a star is mapped on a cosmic chart, but some giants refuse to follow the path. On the Hertzsprung-Russell diagram, the fundamental map of stellar evolution, most stars trace a clear and predictable route from birth to death. Yet supermassive stars are the rebellious outliers, blazing trails that veer wildly off the expected course, leaving astronomers to question the very models that define stellar life cycles. This diagram plots a star's luminosity against its surface temperature, creating a well-trodden highway known as the main sequence, where stars spend the majority of their lives. A supermassive star should enter this sequence as a brilliant blue beacon, and then, as it ages, move predictably to become a red supergiant. But observations consistently catch these titans in places the theory says they should not be. The primary force behind this evolutionary rebellion is their relentless mass loss. A star that is constantly shedding its own weight through ferocious stellar winds is fundamentally changing its own identity. As it ejects mass equivalent to entire planets each year, it is not just getting lighter, it is peeling back its own layers to expose hotter, denser regions beneath. This can cause the star to loop back toward hotter temperatures instead of cooling into a red supergiant, creating bizarre zigzag patterns on the HR diagram that standard models never predicted. The star's rotation adds another layer of complexity. A rapidly spinning star mixes its internal fuel so efficiently that it can appear younger and bluer for longer than a sedentary star of the same mass. Its core remains replenished with fresh hydrogen, effectively extending its main sequence lifetime and delaying its journey to the red supergiant phase. Conversely, a star braked by a powerful magnetic field may evolve more slowly, its internal fires burning less efficiently and causing it to linger in a strange, underluminous state. The most dramatic challenges to theory come from specific stellar rebels. Take the yellow hypergiants like Rho Cassiopeiae. These are enormously luminous stars caught in a volatile transitional phase, pulsating violently and ejecting shells of material. They occupy a precarious, nearly vertical strip on the HR diagram known as the yellow evolutionary void, a region where theory states no star should be able to remain stable. Their very existence suggests our models of internal structure and mass loss are incomplete. Then there are the luminous blue variables like the notorious Eta Carinae. These stars lurch between quiescent blue periods and gigantic eruptions that redden their light, causing them to bounce erratically between opposite sides of the diagram. They are not following a smooth path, they are having a chaotic fit, their evolutionary track looking more like a tangled ball of yarn than a graceful curve. Each of these anomalous giants is a living experiment, forcing us to rewrite the stellar rulebook and reconsider the ultimate fate of the universe's most massive inhabitants. Dust is the last thing you would expect to find near a stellar inferno. These grains of carbon and silicon, finer than smoke, should be instantly vaporized by the intense ultraviolet radiation blazing from a supermassive star. Yet, infrared telescopes reveal a stunning contradiction. Vast, intricate shrouds of dust and complex molecules swirling in the violent space around these giants. This strange survival defies simple physics, pointing to clever cosmic mechanisms that allow creation to persist on the edge of destruction. The first clue lies in the star's own chaotic winds. These are not smooth, uniform outflows, but clumpy, torrential gushes of material. Dense blobs of gas ejected from the star's turbulent surface travel outward. The outer layers of these blobs shield their inner hearts, creating temporary pockets of cooler gas. As this material travels further from the star, it expands and cools rapidly. Within these sheltered, cooler regions, atoms like carbon, silicon, and oxygen can meet and stick together, nucleating to form the first seeds of dust grains. It is a race against time, as the grains must form and grow large enough to withstand the star's radiation before their protective gaseous shield dissipates. The Atacama Large Millimeter Array has mapped this process in stunning detail. Its observations of stars like VY Canis Majoris show vast, sooty clouds rich with molecules like silicon oxide and titanium oxide, all forming in the turbulent wake of the star's own eruptions. Sometimes the star needs a partner in crime. In a close binary system, the gravitational dance between two stars creates a safe harbor. As material is pulled from one star to the other, it doesn't fall directly. Instead, it spirals into a thick, rotating disk around the recipient star. This accretion disk is dense and dusty, and its very structure provides a shadowed region, a cosmic umbrella that protects the forming dust and molecules from the full brunt of the stellar radiation. Here, in the disk's cooler outer reaches, carbon atoms can link into chains and rings, building complex organic compounds right next door to a stellar hellscape. The Spitzer Space Telescope, with its infrared eyes, captured the glow of this paradoxical dust. Its images of systems like Eta Carinae reveal a hot, bright central binary pair surrounded by a massive, cooler cloud of dust that radiates strongly in the infrared. This dust is not a relic from the star's birth. It is a continuously manufactured product, forged in the ongoing conflict between the star's destructive power and its creative, clumpy outflows. This dust does not just linger, it plays a vital role. It acts as a shield, further cooling its surroundings and allowing more molecules to form. It is the raw material for future planets and the very seeds of life, all created in the most unlikely of places. How many other cosmic paradoxes are hidden in the gentle glow of stardust, born from the most violent of cradles? The violent isolation of a runaway star is a drama often born in the most crowded of stellar cities. Within dense star clusters, thousands of stars are packed into a relatively tiny volume of space, creating a gravitational pressure cooker where the supermassive giants living there are forced to behave in bizarre and violent ways. In these stellar metropolises, close encounters are not rare events. They are a fundamental part of life. The core of a cluster like R136 in the heart of the Tarantula Nebula is a seething realm of stellar titans. Hubble Space Telescope images reveal a dazzling, chaotic jewel box with dozens of supermassive stars shining with the power of millions of suns, all crammed into a region that would barely reach from our sun to its nearest stellar neighbor. In such a dense environment, gravitational billiards is a constant game. When two stars have a close flyby, their gravitational interaction can slingshot one of them to incredible speeds. Sometimes, a single, close encounter with a binary star system can disrupt both the binary and the intruder, ejecting one or more stars completely from the cluster. These are dynamical ejections, and they can produce runaway stars that rocket out of the cluster at speeds exceeding the escape velocity, doomed to wander the galaxy alone. But ejection is not the only possible outcome. In the most extreme core collisions, stars can actually merge. When two supermassive stars pass too close, their mutual gravity can pull them together, causing a catastrophic merger that creates a single, even more massive star. Computer simulations of these events show a spectacular and violent dance, with tidal tails of gas being pulled from both stars before their cores finally coalesce. This collision can create a blue straggler, a star that appears unnaturally young and blue compared to its cluster neighbors, essentially resetting its evolutionary clock with a massive infusion of fresh hydrogen fuel. The environment of a dense cluster dramatically shortens the lives of its most massive residents. The intense ultraviolet radiation and powerful stellar winds from hundreds of nearby giants constantly blast each other, stripping away atmospheres and compressing circumstellar disks. This relentless external pressure can peel away a star's outer layers long before it would naturally shed them, altering its evolution and potentially changing the type of supernova it will become. To live in a cluster is to live a life of constant gravitational stress and radiant violence, where a star's fate is not determined by its mass alone, but by the chaotic, unpredictable movements of its brilliant, crowded neighbors. Even the silent vacuum of space trembles with the passage of these stellar giants. Their most profound influence extends beyond light and wind, reaching into the very fabric of space-time to create ripples known as gravitational waves. These are not waves of energy or matter, but literal distortions in the geometry of the universe, stretching and compressing everything they pass through. For supermassive stars, this subtle cosmic drumming originates from any event that creates a changing, asymmetric gravitational field. The most powerful source is the furious dance of a binary pair. As two stellar cores orbit each other, their immense masses churn the spacetime around them, sending out ripples that carry orbital energy away. This slow, steady leak of energy causes the stars to spiral imperceptibly closer over millions of years, their orbital dance slowly decaying in a silent, invisible waltz. But the most catastrophic gravitational wave signal would come from an asymmetric collapse. If a supermassive star's core does not implode in a perfectly spherical manner, if it stutters or jitters during its final collapse, the resulting lopsided explosion would shake the cosmos. A violent, one-off burst of gravitational waves would erupt, a brief but incredibly powerful chirp signaling the death of a titan. We can even detect the subtle hum from the star's own turbulent life. Its non-radial pulsations, those complex surface ripples where one part of the star bulges while another contracts, create a continuous, low-frequency whisper of gravitational waves. While these signals are too faint for our current observatories to hear, the future holds incredible promise. The Laser Interferometer Space Antenna, or LISA, is a planned observatory that will open a new window onto the cosmos. Unlike ground-based detectors that listen for the high-pitched chirps of stellar mass black holes, LISA will float in space, its 3 spacecraft forming a giant triangular interferometer sensitive to the low-frequency rumble of supermassive objects. It is designed to hear the steady, rising hum of inspiraling supermassive binary stars for years before they finally merge, and it may even catch the low thump of a pre-supernova instability deep within a dying giant. To visualize this, picture a still pond representing flat spacetime. Dropping a single pebble creates symmetric, circular waves, but if you spin 2 pebbles around each other before they hit the water, the resulting ripples are a complex, spiraling interference pattern, carrying energy and information about the source. That is what LISA will observe, the intricate spirals written in spacetime itself by these colossal engines. We are on the verge of listening to the universe's deepest rhythms, the hidden music of mass in motion, played by its most massive and mysterious stars. The silent drumming of gravitational waves is matched by a ghostly whisper from the heart of a dying star. As a supermassive star collapses, it unleashes a flood of subatomic phantoms called neutrinos, and the sheer number of these particles is staggering. In the final second of core collapse, a single star can release more neutrinos than there are stars in the observable universe. These are not mere byproducts, they are the primary architects of the explosion, carrying away 99% of the star's gravitational energy in a frantic 10-second burst. This immense energy drain is what allows the core to collapse further, ultimately forming a neutron star or a black hole. The neutrinos blast outward, and their pressure plays a crucial role in reviving the stalled shockwave, helping to blow the star apart. Yet observations reveal a strange anomaly. When we detect neutrinos from these cosmic cataclysms, their energies and flavors do not always match our most sophisticated models. Neutrinos come in 3 types or flavors: electron, muon, and tau, and they can oscillate or change from one flavor to another as they travel. In the incredibly dense environment of a collapsing stellar core, this oscillation is amplified in strange ways. The sheer density of neutrinos can cause them to interact with each other, leading to collective flavor oscillations that can completely rearrange the expected flavor mix by the time they reach our detectors. Our first and only detailed neutrino snapshot from a supernova came from SN 1987A. When that star exploded in the Large Magellanic Cloud, underground detectors on Earth recorded a handful of these ghostly particles. While the detection confirmed the basic theory of core collapse, it also presented puzzles. The neutrinos arrived over a longer period than some models predicted, and their energy spectrum was slightly different than expected. This single precious data set tells us that something is missing in our understanding of the extreme physics inside the collapsing core. It suggests that neutrinos might be transferring energy in ways we have not yet accounted for, or perhaps even interacting with exotic, unknown particles. The next nearby supernova in our galaxy will deliver a flood of neutrino data, allowing us to read the star's death certificate in unprecedented detail. Each flavor of neutrino tells a different part of the story, with electron neutrinos dominating the initial burst from the neutronization of the core, and all flavors carrying away the thermal energy of the cooling remnant. Why did the neutrinos from 1987 behave the way they did? And what other secrets about the fundamental forces of nature are these ghostly messengers waiting to reveal? The silent flood of neutrinos marks a star's final surrender to gravity, but the corpse left behind can be a cosmic monster of a completely different class. We have long known of stellar mass black holes, the dense remnants of stars up to a few dozen times the Sun's mass, and the supermassive black holes that lurk in galactic cores, weighing millions or billions of solar masses. The gap between them has been a profound puzzle, a missing link in the black hole family tree. The collapse of a supermassive star might be the direct forger of these intermediate mass black holes, bridging the divide in a single violent act. The key ingredient for this formation is a pristine environment, one with very low metallicity. In the early universe or in certain dwarf galaxies today, stars can form from gas that is almost pure hydrogen and helium, lacking the heavier elements that act as a coolant. In this simpler chemical soup, a collapsing cloud of gas can avoid fragmenting into many smaller stars, instead coalescing into a single, truly monstrous star, perhaps several hundred times the mass of our Sun. When such a titan reaches the end of its life, it faces a critical threshold. If its final mass is between roughly 100 and 100,000 solar masses, its core collapse may bypass a supernova entirely. The gravitational pull is simply too overpowering. There is no explosive rebound, no shockwave to blow off the outer layers. The entire star implodes, its entire structure falling inward in a direct collapse, leaving behind a black hole with a mass squarely in that elusive intermediate range. Evidence for this process is now emerging from the whispers of spacetime itself. Gravitational wave observatories like LIGO and Virgo have detected mergers between black holes whose individual masses fall directly into this intermediate category. These are not the tiny remnants of ordinary stars, but the potential direct descendants of primordial supermassive stars. The remnants of hypernova, those incredibly energetic explosions, also provide clues. The sheer power of a hypernova and the lack of a bright supernova remnant in some cases point toward the formation of a hefty black hole, one that greedily swallowed most of the collapsing star's mass without a significant visible outburst. These black holes are the silent giants, the missing links that could have served as the seeds for the supermassive black holes we see today, growing over billions of years by devouring gas and merging with others. The death of a single ancient star may have planted the seed for an entire galactic empire. The invisible ocean of dark matter that fills our galaxy may hold another secret, a subtle but profound interaction with the universe's brightest giants. While dark matter famously refuses to interact with light, its immense gravitational pull and potential particle nature could directly influence the life and death of a supermassive star. Theoretical models suggest that if dark matter particles are their own antimatter counterparts, a property known as being Majorana particles, they could annihilate upon contact deep within a star's core. Imagine a supermassive star forming in a region dense with dark matter, perhaps near the center of a galaxy. As the star moves, its enormous gravity would pull in a steady stream of these invisible particles. Once inside the stellar core, the incredibly high densities could cause the dark matter particles to collide and annihilate, converting their mass directly into pure energy according to Einstein's famous equation. This would inject a powerful new heat source right into the star's heart. This extra energy from dark matter annihilation would act like a hidden furnace, supplementing the star's nuclear fusion. The consequences would be dramatic. The star would become far more luminous than standard models predict, shining with an unexplained excess of energy. It might also live significantly longer, as the dark matter heating could support the core against gravitational collapse, delaying its ultimate fate. Some theories even suggest that in extreme cases, this process could alter the type of supernova the star produces, or prevent it from exploding entirely, leading instead to a direct collapse into a black hole. The observational signature of such a star would be a clear anomaly. Astronomers would measure a star with the temperature and size of a typical supergiant, but its luminosity would be off the charts, placing it as a glaring outlier on the Hertzsprung-Russell diagram. Its light curve might also show strange, long-term variations tied not to internal pulsations, but to the density of the dark matter environment it is passing through. While no star has been definitively identified as a dark matter engine, the search is on. Scientists are using the most advanced stellar models to predict what such an object would look like, and telescopes are scrutinizing stars in regions of high dark matter density, like the galactic center, for any that shine a little too brightly for their own good. Could the brilliant light of a supermassive star be fueled in part by the annihilation of the universe's most mysterious substance? The environment a star is born in writes its destiny from the very first moment. A supermassive star forming in a metal-poor dwarf galaxy, a relic from the early universe, lives a life utterly unlike its cousin, born in the metal-rich spiral arms of a galaxy like our own. The word metal here means anything heavier than hydrogen or helium, and this single factor dictates everything. In a pristine dwarf galaxy where the gas is simple and clean, star formation is a blunt, inefficient process. Without complex molecules to help cool the collapsing gas clouds, they fragment less easily, leading to the birth of far fewer stars, but those that do form can grow to truly monstrous proportions. These are the potential seeds for intermediate mass black holes, stars that begin their lives with a staggering advantage in mass. Their evolution is a rapid, violent burn. Critically, their extreme mass loss through stellar winds is significantly weaker. Metals are incredibly efficient at absorbing a star's intense light and using that energy to drive a wind. In a metal-poor star, the wind mechanism is less effective, like a fire hose with lower pressure. The star holds onto its mass more tenaciously, burning through its fuel at a ferocious rate but remaining heavy right up to its dramatic end. This leads to a very different death. A metal-poor supermassive star is far more likely to end its life in a paired instability supernova, the complete self-annihilation that leaves no remnant, or to collapse directly into a massive black hole. We see evidence for this in the faint, ancient dwarf galaxies orbiting our own, where the chemical signatures of past supernova point to these uniquely powerful explosions. Now contrast that with a supermassive star born in the crowded, metal-rich disk of a spiral galaxy. Here, the star formation process is efficient and prolific, but it also produces more stars of lower mass. The supermassive stars that do form are immediately bathed in a complex chemical soup. Their powerful winds are supercharged by the abundance of metals in their own atmospheres. They shed their mass at an incredible, almost frantic pace, peeling back their own layers to expose their hot interiors long before their cores collapse. This relentless weight loss program changes their entire evolutionary path. They are less likely to reach the extreme masses required for a paired instability event. Instead, their lives are dominated by their own self-inflicted erosion, often leading them to become brilliant Wolf-Rayet stars, their hydrogen envelopes stripped away to reveal the helium and nitrogen burning beneath. When they finally die, their core collapse supernovae are different. enriched by the complex chemistry of their birth cloud and shaped by the mass they have already lost. Observatories like the Hubble and James Webb telescopes are now comparing these stellar lives across the cosmos. They look at a dwarf galaxy like Zwicky 18, a nearby example of a metal-poor environment, and see stars that behave like the ancient pioneers of the cosmos. Then they turn their gaze to the Tarantula Nebula in the metal-rich Large Magellanic Cloud, witnessing the furious winds and complex nebulae of stars living fast and dying young in a chemical paradise. The same fundamental physics plays out in radically different ways, proving that a star is not just a product of its mass, but a child of its galactic home. The brilliant death of a hypernova does more than tear a star apart. It forges the very elements that make up our world. Deep within those relativistic jets, where matter is churned at temperatures of billions of degrees and densities beyond comprehension, nature runs its most extreme alchemy, a frantic process known as the rapid neutron capture process, or the R process. This is the primary cosmic factory for the heaviest elements in the universe, including gold, platinum, and uranium. The key to the R process is an overwhelming flood of free neutrons. In the chaotic environment of a collapsar, as the star's core collapses into a black hole and powers the jets, neutrons are ripped from atomic nuclei in staggering numbers. These free neutrons then bombard nearby seed nuclei like iron at an incredible rate. The capture happens so rapidly that the nucleus does not have time to stabilize through radioactive decay before another neutron slams into it. This forces the nucleus to grow heavier and heavier, climbing the periodic table in a matter of seconds to form elements that are otherwise impossible to create in the steady burn of normal stellar fusion. The specific conditions within the hypernova jets are perfect for this. The material is not only incredibly neutron-rich, but also extremely hot and dense, allowing the frantic neutron captures to proceed until the nuclei become so heavy they fission or the material expands and cools, freezing the newly forged elements in place. For a long time, astronomers believed that neutron star mergers were the sole dominant source of these R process elements. When two neutron stars spiral together and collide, they indeed spray neutron-rich material into space, creating a similar, prolific R process environment. The gravitational wave event GW170817, which was accompanied by a brilliant kilonova, confirmed that these mergers produce vast amounts of gold and platinum. However, the story is more complex. The sheer number of heavy elements in the universe, particularly in very old stars that formed early in cosmic history, suggests that another, faster source must have been at work. Hypernova from supermassive stars are perfect candidates. These colossal explosions were far more common in the early universe than neutron star mergers, which required two stars to live long lives and then spiral together over billions of years. A single, dying supermassive star could have seeded its galaxy with heavy elements almost instantly after its formation. The debate now centers on which site contributes more to the cosmic inventory of gold. Is it the violent, rare embrace of two dead stars or the cataclysmic death of a single, living titan? The answer likely lies in a combination, a cosmic division of labor where both these extraordinary events work together to fill the periodic table. Every piece of gold on Earth carries the echo of a universe-shattering explosion, a relic from a jet of fire that once screamed from the heart of a dying star. Even the most crowded stellar cities hold onto their deepest secrets. Within the brilliant confines of supermassive star clusters, astronomers confront glaring questions that challenge our fundamental understanding of how these giants form and die. The first great puzzle is the upper mass limit. Is there a physical ceiling to how massive a star can be? In clusters like the Arches cluster, nestled near our galaxy's turbulent center, we find stars pushing 150 solar masses. But theory suggests they could have been born even heavier, raising the question of whether some fundamental process, perhaps tied to the onset of pair instability, caps their birth weight. Recent observations from the James Webb Space Telescope are intensifying this debate. By peering through the dust in star-forming regions like NGC 336, JWST is identifying protostars so bright and so embedded that their initial masses are difficult to pin down. They might be single behemoths nearing 200 solar masses, or they could be tight, unresolved multiples that merely mimic a single titan. This ambiguity lies at the heart of the mystery surrounding the initial mass function, the cosmic rulebook that dictates how many stars of each size a cloud of gas will produce. Does this rulebook have an upper cutoff, or does it simply make stars this large incredibly rare? The fate of the most massive cluster members is equally contentious. In a dense environment, a star's life is a gamble. Will it be ejected as a runaway before it can explode, or will it collide and merge with a neighbor, creating an even more massive object that defies standard evolutionary tracks? Some theories suggest the ultimate products of these clusters are not standard stellar mass black holes, but the elusive intermediate mass black holes, the missing links between stellar and supermassive giants. The violent lives and deaths of these clustered stars are written in the chemical makeup of the gas around them. When one explodes, its supernova ejector slams into the winds and radiation of its still living neighbors, creating a complex, polluted environment. Decoding this chemical soup may hold the key to understanding which stars lived there and how they died. The very existence of these clusters, blazing with impossible brightness, forces us to wonder if we are seeing the full story, or if the true monsters are hiding just beyond the resolution of our most powerful telescopes. The final, frantic collapse of a supermassive star might be the source of the universe's most enigmatic signals. Fast radio bursts are incredibly brief, intensely powerful flashes of radio waves that travel across billions of light years, and their origin has been one of astronomy's greatest puzzles. One leading suspect is the birth of a magnetar, an ultra-dense neutron star with a magnetic field 1,000 trillion times stronger than Earth's. When the core of a supermassive star collapses, the resulting neutron star can be born spinning at a significant fraction of the speed of light. This rapid rotation, combined with an unimaginably powerful magnetic field, creates a dynamo of catastrophic potential. Theorists propose that this newborn magnetar can experience starquakes, sudden fractures in its rigid crust that release colossal amounts of energy, shaking the magnetic field and producing a single, brilliant fast radio burst. The energy released in a single millisecond of one of these events can outshine our sun for an entire day, but the story may not end with a single quake. Some fast radio bursts have been observed to repeat, flashing again and again from the same patch of sky. This points to a source that can survive its own cataclysm, like a magnetar in a dense, chaotic environment. Imagine a young magnetar, the remnant of a supermassive star, plowing through the dense shell of material its progenitor ejected before the final explosion. As this material falls back onto the magnetar, it could trigger repeated magnetic reconnections, each one unleashing another burst. Observational evidence is beginning to tentatively link these cosmic sirens to stellar environments. One notable repeating burst was traced back to a region of active star formation in a spiral galaxy, exactly the kind of place where supermassive stars live fast and die young. The specific galaxy was metal-rich and bustling with stellar nurseries, a fitting cradle for the kind of star whose death could create such a magnetic monster. Yet, this is frontier science and other explanations compete. Some models suggest fast radio bursts could come from the merger of two neutron stars or from material accreting onto a black hole. The challenge for astronomers is that the bursts are so fleeting, appearing and vanishing in an instant, making them incredibly difficult to pinpoint and study. New telescopes like the Canadian CHIME array are now scanning the entire sky daily, catching thousands of these events and slowly building a statistical map of their origins. Each new detection is a clue, a piece of a cosmic puzzle that may ultimately be solved by understanding the violent, magnetic deaths of the universe's most massive stars. What other transient mysteries flickering in the darkness are the final signatures of these stellar titans? From runaway stars to pair instability supernova that leave no corpse behind, these 30 strange behaviors paint a portrait of cosmic giants that refuse to follow the rules. They challenge the very foundations of stellar physics, from the mass luminosity relation to the predictable paths on the Hertzsprung-Russell diagram. Each tantrum, each flicker of light, and each violent eruption is a piece of a puzzle we are only just beginning to assemble. Our understanding of these titans is being rewritten in real time, fueled by data from observatories like Hubble, Chandra, and the James Webb Space Telescope. Yet for every mystery solved, a dozen more emerge from the darkness. The next generation of telescopes, from the Gravitational Wave Observatory, LISA, to the extremely large telescope on the ground, will listen to the ripples in space-time and peer into the hearts of stellar nurseries with unprecedented clarity. They will hunt for the ghosts of dark matter engines and capture the final moments of a hypernova in exquisite detail. The story of supermassive stars is far from over. It is a living, breathing field of discovery where you, the viewer, are a witness. The cosmos is full of wonders waiting to be uncovered. What cosmic mystery captivates you the most? Share your favorite in the comments below. And if you are eager for more journeys to the edge of our understanding, be sure to subscribe for more explorations into the secrets of space.